In this section, we'll talk about some common applications for integration in a physics course, and one of those is work. So work in the physical sense is measured by, or it happens whenever an object is moved through a distance. So for instance, if you have like a box or something, all right, and you move this box from an initial point over to an ending point. So if we move it through this distance here, then work is said to be done. So whatever the distance is, maybe this is 50 meters, and whatever the weight of the box is, and weight here is going to be measured as a force because we're looking at how much the object weighs with respect to gravitational constant. So this would be like in newtons. So maybe this is 30 newtons is the weight of the box, and then we move it 50 meters. Then the amount of work done here is the product, 30 times 50, which would be 1,500 Newton meters, or joules. So joules is the common unit of work. And in the other system, you also have foot-pounds. That's pretty common, but joules is the standard. All right, but the thing to know is that work happens whenever you move an object through a distance. Now, let's complicate things a bit more. Let's suppose we have a variable force. All right, so the amount of force changes while this is happening. So maybe this box contains a liquid, okay, but there's actually a leak, all right, and so there's a hole in the bottom and it's leaking out liquid. All right, so as that leaks out liquid, the weight of the box is going to decrease. And so it's going to be easier to move. So there might be like a variable amount of force necessary to move it. So that is something that we can measure using approximations. So for instance, we have like our starting point and our ending point, for instance. And then we're going to move the box through this distance. Okay, but of course our box is leaking, so it's leaking water, the whole time. So the level of the water decreases and the weight of it decreases as well. So what we can do is we can take a look at, what does the box weigh initially? So how much force does it have? And then see what happens maybe just a little ways down. So like at some point x sub 1. Measure the weight of the box, and then that would see how much force was required to push it to that point. And then check it out at another point, and another, and so forth. So if we continue determining how much work is necessary to move from one point to the next, then what we can do is add up the work on each subinterval, because the work on this first subinterval would be the force required on that first subinterval times the distance that we traveled. So like I could say like x1 minus x0 would be the distance traveled. All right, and then the amount of work required to move it on the second subinterval would be the force required. So water has drained out, so it weighs less, so that force has decreased. And then we would see multiply that by the distance, and so forth. And we would continue doing this for all the subintervals, and then we can say effectively the amount of work on the ith subinterval is going to be the force required to push it at that ith subinterval times x sub I minus x sub I minus 1, which is probably starting to get a little bit commonplace at this point. So this is effectively like if I thought of the force as a function, so the amount of force required at the ith subinterval times the width of that subinterval. Then what I can do is I can approximate the total work by summing up the work on each subinterval. And when I add up the work on the subinterval, I've got the total work across the entire interval. Now, another thing that's probably getting fairly common is if you add up all the work over each subinterval, but then you allow the subinterval widths to decrease to 0, or we let the number of intervals increase to infinity, that means the same thing. Then, when we're taking the limit of a sum, we can use integration instead. So we can define work by a variable force through this formula right here. So work done by a variable force is calculated by this integral. And all we need to do to use this is find some function that represents the force for whatever application we're doing required at any point in time. Okay, let's take a look at some examples. Now, one example that's pretty common to use this for is Hooke's law. And Hooke's law deals with springs and how much force is required to stretch a spring or to compress a spring. And it states that according to Hooke's law, the force required to compress or stretch a spring from equilibrium is proportional to the distance that the spring is already compressed or stretched. So therefore, we have the force required to stretch a spring is some spring constant k times x, the distance that it's already been stretched. All right, and thus, as you continue to stretch it out, it gets harder and harder to stretch it even further. So the force increases with more distance. Okay. So it's kind of like this. It's like we have I'll draw, there's a spring. All right, we have a starting point, which the spring is completely at rest. It's not even opened at all. And as you stretch it, and you stretch it some, beyond its equilibrium, it's going to take a little additional force to get, this distance here. All right, so to get it to x1. But it's stretched a little bit, which means it's going to be even more difficult to stretch it out to another point down the way, x2. So it's going to require some new force to move it that much further, and so forth. So as we go out here to the end point, it will take more and more force. So that's where this function here comes from, measuring the amount of force for us. Now, we do need to know this spring constant. So the thing is, most of these problems will either say, it will give us basically a snapshot. So let's say we have a snapshot at like x2, and this is A is at rest, x2 is like 0.5 meters, okay? They might say it requires, so a spring requires 20 newtons of force to stretch to 0.5 meters. Okay, so this is like a snapshot just here at this one particular point. So we know exactly how much force is required to move it here. And because it's proportional at all other points, this constant is the same, we can then predict what the amount of force is from there forward. And from this, we can use the snapshot to say that the force of 20 newtons is the spring constant times 0.5. All right, so that tells me force is equal to the spring constant times the distance it takes to move it. So what we would do is divide both sides by 0.5, and that should tell me that this spring constant is, what, 40? So that gives us a way of determining a function, f of x, which would tell me the amount of force required to move the spring at any distance. All right, so that's going to be two very prominent step in many of these problems. It is possible that a problem might just give you the spring constant to start with, but very often you'll have to first calculate the spring constant. So you'll find that using the same formula, but it's just one point in time. And then you'll calculate the total amount of work using the integral stated above. So now that we have f of x, which is k times x, we can now integrate and get our answer. So let's see how this is all done with an example problem. Suppose it takes 10 newtons to compress a spring 0.2 meters from the equilibrium position. How much work is done to stretch the spring 0.5 meters from the equilibrium? Okay, so we're always going to have this hint about some snapshot. All right, so how much force is required to move at a certain distance. And that enables us to figure out the spring constant K. So we just use force equals K times the distance required to move it. And for this one particular point in time, the force is 10 newtons to move that spring 0.2 meters. Then if I divide both sides by 0.2, I can then determine that the spring constant here would be, looks like 50. Now, the total work done, that's the next part here, how much work is done to stretch the spring 0.5 meters from the equilibrium. So the total work to stretch that 0.5 meters, that would be the integral. We're going to go from the starting position to the ending position, so from rest up to 0.5 meters. Now sometimes the question will say how much work is done to stretch it an additional 0.5 meters, and that means you would just start at 0.2 and then go to 0.7. So be careful in the wording. But this is saying 0.5 meters from the equilibrium, so from 0 to 0.5. And then it's going to be our function f of x, which the force required to stretch the spring at any point is going to be k times x. So that's going to be 50x dx. And of course, you're free to use fn int. Some of these will probably be easy enough that you might just choose to integrate. Either way is no big deal. So integral from 0 to 0.5, and that's going to be 50x dx. So the total amount of work here is 6.25 joules. Another example. Suppose it takes a force of 8 pounds to stretch a spring 6 inches from the equilibrium position. How much work is done to stretch the spring 1 foot from the equilibrium position? All right, so here's our snapshot. And that allows us to calculate the spring constant. So to get that, we use the amount of force required to stretch it some particular distance. So it's 8 pounds of force, and the distance is 6 inches. Now do be careful, because this being in inches and this being in feet, these are different measurements, and so you want to make sure you get those written both in terms of the same measurement and then answer in the same value. Now, it's more common to see work measured in foot-pounds than in like inch-pounds, so we'll use feet. So 6 inches is 1/2 of a foot. So 0.5, then we just need to divide both sides by that. So 8 over 0.5, I think that just doubles it, right? Yeah, so that's 16. And then the next step, calculate the total amount of work done. And that work is going to be, so we want to know how much work is done to stretch the spring 1 foot from the equilibrium. So it's the integral from 0 to 1 of 16x dx. And we can just use the calculator there. 0 up to 1, 16x dx. So that looks like it is 8 foot-pounds.